So we start with the magnetic field. So this is the beginning of the subtopic that is called the magnetism. So under the magnetism chapter, there are two topics. One is called the magnetic field and another the magnetic force. So first we calculate the magnetic field, and for that you should learn one law which is known as the Biot-Savart Law. Okay. So to deal with that, so we do an experiment. So let us say there is a current carrying wire. Through this wire the current is being flowing. Okay. So once the current carrying wire is carrying a current, so you know that there is something around that takes place, so which is known as the basically magnetic. So this current carrying wire is producing a magnetic field. These magnetic field lines are basically circular in loop type situation, where I can say the magnetic loop fields are moving in this direction. How to ensure the direction? So for that, once I place a magnetic needle or compass, so that compass will show the reflection. Okay. So it has been observed that whenever a current carrying wire is there, so now we put a magnetic needle in front of this wire, then the needle is showing the deflection. So needle shows the deflection means there must be some kind of force acting on the needle, and that force comes due to the presence of the magnetic field. Okay. So first we discuss about the magnetic field. Now for that there is a law or the experiment that has been performed by the scientist Weston. What he does basically, so he put a wire, and through this wire he allow the current, okay, by making the contact. So once I contacting the circuit, that means now the circuit is closed, so current is being flowing through this wire. And once I flow the current, so you observe that if I place a magnetic needle, so this is the magnetic compass placed below the wire. So once I touch it, that means now the current will flow and the deflection will be observed inside this needle. So needle will rotate. That means there must be something amount of force is acting on this needle, and that has been explained by the scientist Weston. So the outcome of the Weston experiment is what? So if I say there is a current carrying wire and there is a charge it is placed near about this current carrying. When the charge is at rest, so if I say this charge is at rest, so that means now no force is acting on this. Why? Because the charge is at rest, that there is no deviation. So if it is at rest, it remains in rest condition. So there is no movement of the charge when the charge is at rest. Now, second situation is that when the charge is projected, now we project the charge particle with certain velocity v, and you observe that the deviation takes place. That means the particle will bend like this. Okay. So bending takes place, that means the deviation is occurring, and that means once the deviation is there, that means I can ensure that some amount of force is acting on that particular part. Why? Because once we apply a force, then that particular force may increase the velocity or may decrease the velocity or may change the direction. In this particular situation, since the deviation is occurring, and once we closely observe the situation, that now we find that the particle is moving with the same speed. Okay. So at any instant of time, what I am observing that the particle is not changing its speed. So the force is not changing the magnitude of velocity. So what it does basically, it will only change the direction. So if force is acting on the particle, why? Because the direction is changing, the deviation is occurring, but that force is not able to change the velocity of the particle, or I can say the kinetic energy of the particle is constant. So there is no change in the kinetic energy. Now this force must be acting in a direction which is perpendicular to the direction of the flow. If the force is acting at an angle other than 90 degrees, let us say there is a particle which is moving with a velocity v in this direction. Now I am applying a force which is making an angle not equals to 90 degrees with that. So let us say this is the alpha. So component of force will come along this direction. So F cos alpha will come. Now this F cos alpha will certainly increase the velocity of the particle. Okay. So that means if the particle is observed that the velocity is not changing, that means now I can conclude that the force that is acting, it should be perpendicular. Yeah, the force is perpendicular to the direction of velocity. This is the third observation. Now, important observation is the fourth one. The fourth one says that the force cannot be electrostatic in nature. Why? Because if the force is electrostatic in nature, then that force is observed in the situation number 1. When the particle is at rest, I observe that there is no deviation. That means there is no force is acting. So if that force is there, that means the particle should observe or feel some kind of force which is electrostatic in nature, then it will show some kind of deflection. But it is not showing the deflection when the particle is at rest. That means that particular force cannot be an electrostatic force in nature. Now, last one is the behavior of the charged particle is exactly similar to the magnetic needle used in the experiment. Okay. So what is the behavior? So if I say that the particle is projected and the particle is bending like this, deviation. So now if I place a magnetic needle in this particular path, so magnetic needle will also show the direction in which the particle will bend. So this is the compass needle. So compass needle also exactly shows the same direction in which the particle will bend. That means now this behavior of this magnetic needle is similar to the situation of the particle. That means now I can say that the needle is observing some kind of force. So that means this particular force should be magnetic force in nature. Okay. So since the behavior is exactly similar to the magnetic needle, that means the force acting on this particle is the magnetic force. And again, the force is always perpendicular to the direction of velocity. So if I say initially the particle is at point 1, ASA, so at this point the force is acting towards this direction. Here the particle force is this direction, here the force is this direction. So every time the force is acting perpendicular to the direction of the velocity, that means now this particular force cannot be helpful to increase the speed. That means its speed remains constant and it can only change the direction. So these are the basically findings of from the wasted experiment once you allow the current to flow through a current carrying. So now, based on this observation, entire chapter is divided into two parts. Entire chapter is divided into two parts. First is the how much magnetic field is being produced due to the current carrying. So I observed that when the particle is being projected, so there is a deviation of the particle. So particle will bend like this. So bending takes place means that means some kind of force is coming into the picture. Now why the force comes? Because before the force, the field is existing. Okay. So current carrying wire is producing some kind of magnetic field. So magnetic field is a vector quantity. We represent it with a V vector. So I want to know how much amount of V is being produced and what is the direction of that also. And second one, I want to calculate how much force is exerted on the charged particle. So I want to calculate this force that is called the magnetic force. Okay. So there are two requirements. I have to calculate the magnetic field as well as the magnetic force. Okay. So both are the vector quantity. The direction of both the force or the magnetic field has to be understood properly and the magnet. Now first part is the calculation of the magnetic field. So in order to calculate the magnetic field, or rather we say the direction of the magnetic field, we prefer to use the right hand thumb. Okay. So what it says that if I allow the current to flow in any direction, let us say the current through this coil. So later on we will understand this coil is known as a solenoid coil. So if I say the current is being flowing along the red arrow direction in this direction. So if I curl my right hand fingers along that direction and the direction of the thumb will be in this direction. So this direction, that is the direction of thumb, will define the direction of magnetic field. Okay. So this is basically the calculation or the method to calculate the direction of the magnet. I don't know what is the amount of magnetic field or what is the magnitude of the magnetic field, but I want to calculate the direction of the magnetic field. So for that, I have to curl the finger of the right hand along this current direction. And once I curl this along the current direction, then if I place my right hand, so right hand thumb will give the direction of the magnetic field. Now this is for the loop. This is for the loop. If I say the loop is not like this here, if I say any kind of loop may be there, let us say there is a circle. Okay, there is a circle loop. So let us say I say the current is going in this direction. So if I curl my finger along the I direction or the current flowing direction, and if I place my thumb, the thumb is pointed towards inward. So magnetic field will be inward. If I say the same loop is represented by a triangular loop like this way. Now if I say current is going in this direction, okay. Again if I curl my finger along this direction, so thumb will be pointed inward, so into the plane of paper. So like this way, once I rotate my finger or curl my finger or right hand along the current direction, then the thumb will give the direction of the magnetic. So that particular method is used to calculate the magnetic field for a current carrying loop. The loop means it is a closed kind of loop. So through that loop, when the current is being flowing, I have to curl my finger along the direction of the current and thumb will give the direction of magnetic field. But similarly, if I say for a wire part, so I have to change my some situation is like this. Let us say this is the positive end of the battery, this is the negative end of the battery. So current is being flowing in this direction. So through this wire, the current is coming down. I use down. Now for a wire, now instead of curling the finger, I have to place my thumb along the eye. So place the thumb along eye direction. And if I curl my finger, then the downward thumb will give a curling situation like this way. So I can observe there is circular ring-like structure is being formed. So these are basically rotating in this direction. These are rotating in this direction because the curling sense will be in this direction. So that gives the direction of the magnetic field basically. So this is how I have to calculate the direction of the magnetic field for either the loop or the current carrier. But for before that, I should also know how to calculate the magnitude. So magnitude of the current magnetic field has to be calculated based on the law which is known as the Biot-Savart. Okay, so these are the two scientists who arrived at this particular result based on certain experiments. So it is a purely experimental result. Now what it says that there is a current carrying wire through which let us say I amount of current is being flowed. So now on this particular wire, you consider two different points which are very, very close to each other. Let us say this is the point A and this is the point B. So A and B are basically the points on the current carrying wire. So AB length is known as the DL vector. So DL is what? This is the elemental length or a small element of AB. AB is called the DL vector and DL vector multiplied by I. So if I use I into DL vector, so this means this is called the current element. This is called the current element. So I choose a small current element on the wire itself and let us say this is the point, center point of this current element O. So from O I want to measure what is the magnetic field at point P. What is the P point? P is the point which is located at a distance of R from the O point. So this vector is known as R. OP vector is our R vector. OP vector is basically our R. So I want to calculate what is the magnetic field at that particular point P. So for that I have to use the Biot-Savart. So what this law says that the small magnetic field produced at that particular point is proportional to I. That means if I increase the amount of current, then that particular magnetic field produced at this P point is known as the dB magnetic field produced. So the amount of magnetic field produced at this particular point P is dependent directly proportional to the amount of current flowing to the current carrying wire. If I increase the I value, then the magnetic field strength will increase. If I decrease the current value, then the magnetic field strength will decrease. Now, second observation is that it depends on the length also. If I increase the element length DL, if I increase the element length DL, then what we observe that again the magnetic field at point P will increase. If I reduce the DL value, then the magnetic field at point P is decreasing. Now, third is the important observation is that dB is also proportional to sine theta. What is sine theta? The theta is the angle between the DL vector and the R. So, in this particular situation, DL vector is, let us say, this is the DL vector. Okay. And from this point, I draw the R vector. R vector. So, the angle between the DL vector and R vector is known as theta angle. So, it depends on the sine theta. Or directly proportional to sine theta. And the fourth observation is that dB is also inversely proportional to R. What is R square? R square is nothing but the basically mode of R. So that is the distance of the point O, the point P from the point OP vector mod is called the R vector. So if the point P is closer to the wire, then the magnetic field is going to increase. That's why it's called the inverse proportion. If the point P is away from the wire, then the magnetic field strength will be reduced. So these are the four important observations that has been done by the Biot and Savart, two scientists, based on certain. Now we combine this all the four equations together to get the truth. Okay. Now once I combine this, what I am getting that initially I write dB is proportional to I amount of time. So dB is directly proportional to dL. dB is proportional to directly proportional to sine theta. So these three are indirect proportion. And the third one is the dB, which is inverse proportional to R. So these are the four important observations from the Biot-Savart law. And if I combine all those four parameters, So that means I can write dV is proportional to I dl sine theta divided by r square. Okay, so this is the final result of the Biot-Savart Law. dV is proportional to I dl sine theta by x. Now, in order to equate, in order to put the equal into sign, or I use a constant. That constant is known as the mu naught. That constant is mu naught. So mu naught by 4 pi is basically the constant. So mu naught by 4 pi into I dl sine theta by x. Now what is mu naught? So mu naught is similar to our epsilon naught used in the electrostatics. So mu naught is basically the permeability. Permeability. So what is permeability? Permeability is the ability of the medium to transfer or propagate the magnetic field. Similarly, we define the permittivity. So permittivity is the ability, how fast or the ability of the medium, so that it is how fast or how slow the electric field will be propagated. Here I am discussing about the magnetic field. So how fast the magnetic field is being propagating, depending on that, the mu naught value is given. So mu naught is one constant number. So again mu naught by 4 pi is also another constant number. So if I put this constant proportional to constant, so ultimately I am writing the equation with the proper equality sign. So that is the final form of the Biot-Savart law, where I am using this equation. I am using this equation that dV equals to mu naught by 4 pi into I dl sine theta by x. Okay. What is mu naught? Mu naught is called the magnetic permeability or vacuum of free space. Either I can place this wire in a medium, which is basically the air, or in a vacuum kind of situation, or there is a free space. So it measures what? It measures the ability of the material to allow the magnetic field pass through. So mu naught by 4 pi number is basically a constant number, that is 10 to the power minus 7 is a value. Now regarding the unit, so for magnetic field we use the unit as Tesla. Tesla is the unit for the magnetic field. So mu naught has the dimension of what? Tesla into meter square. So if I write mu naught, so mu naught should be equal to dV into r square divided by I into dl, and sine theta is there and 4 pi is there. So both of 4 pi and sine theta has no dimension. Only the dV is Tesla. This is Tesla. Then r square is meter square divided by I is ampere and dl is meter. So ultimately 1 meter will cancel out. So we are need to Tesla into meter by amp. So that is the dimension for the mu naught. The mu naught is equal to how much? 10 to the power minus 7 into 4 pi, or 4 pi into minus 7 Tesla meter per amp. Okay. So this is the constant value. So we have to remember that constant number. So this is the final form of the Biot-Savart law, but we have to modify this particular. Okay, I cannot use this law directly. I have to write in some other form. So what is that format? That is the format of cross product. So what is the value that I am getting? That before applying the cross product rule, let us say I am getting the result as mu naught by 4 pi I dl sine theta divided by r square. Okay. So now I want to apply the numerator part is almost similar to our cross product formulation. A cross B is AB sine theta. So I dl sine theta is similar to cross product formulation. But I is a scalar quantity. I is scalar. So now if I multiply numerator by r and divide by denominator by r, then I can write it as mu naught by 4 pi I into dl into r into sine theta divided by r cube. Okay. Now dl is one vector, r is one vector. So a cross b is the formulation. So basically the numerator is giving the feeling that mu naught by 4 pi into I into, instead of writing dl r sine theta, I can write dl vector cross r vector. But since I am using the mod part, so I have to write it mod part divided by r cube. So that is the dV value that has been obtained from the Biot-Savart law in the form of cross. Okay. So in order to find the direction, I have to follow this dl cross r direction. So numerator is the cross product value. So I have to take the mod of that cross product, and in order to find the direction, I have to follow the dl cross r. So what is dl? dl is this distance. So this distance is dl vector. Yeah, this distance is dl vector. So dl vector cross r vector. So r vector is in this direction. So dl cross r. So if I place my thumb along the DL direction and stretch the right hand fingers along this R direction. So face of the palm will be outward. So outward means dot. Okay. I am placing my thumb along the DL vector, right hand thumb along the DL vector and stretch the fingers along this R direction. So the DL cross R, that is the direction of the D vector at point P, will be out of the plane, that is dot. Similarly, if I locate another point, on this particular DL length on this direction, let us say I am getting this is the R vector, another vector, let us say this is the Q point. Okay, so for this is our DL vector. So now if I place the thumb along the DL vector and cross the fingers or stretch the fingers along the R direction, now the palm face will be into the plane of paper. So on all the points which are on the right hand side of this square are giving the direction of the magnetic field, all are cross. Similarly, all the points which are on the left hand side of the wire are giving the direction of the magnetic field, which is basically dot. Okay. So finally, what I can conclude that a current carrying element or a current carrying wire will separate the magnetic field on both sides of the wire in two different regions. One region either a cross magnetic field, another region should be dot magnetic field. Okay. So this is the way I have to apply that Biot-Savart law in their vector format, or I should apply the Biot-Savart law in scalar, because direction has to be obtained from the cross product. So this cross product will be the direction value, and once I am applying the calculate the magnitude, I have to apply it in mod formula. So this is the formula that we apply to calculate the magnitude of dB. Okay. And in order to find the direction, I should follow the cross product rule. So this is basically the formation of the Biot-Savart. Now, this Biot-Savart law can be written in another format. What is that format? Now, in the denominator, there is R cube. That R cube is basically the mod of R vector. Now, instead of writing R vector, so I can write R vector. Any vector can be written as the mod of this number into any vector. So what is that number? That small r is writing for the mod part. So any vector can be written as a product of magnitude multiplied with the unit vector. So now I can use this formula to replace the equation. So dV vector can also be written as mu naught by 4 pi is the constant number multiplied by I. So multiply dl vector and cross r vector. So what is r vector? R vector is basically r into r divided by r cube. Now this r will cancel out. So ultimately we are left to mu naught by 4 pi I into dl vector cross r cap divided by r square. Okay. So this is another way of writing the Biot-Savart law in the form of unit vector. So in the numerator I am doing the cross product of dl cross r and the denominator becomes r squared then. Okay. So this is another formula that we should use for the calculation of dV vector. But most popularly I use to calculate this dV number by this equation number 1. Okay. So I use equation number 1 to calculate the magnetic field for a current carrying wire or for any type of geometry. Okay. So regarding the mu naught by 4 pi, the mu naught by 4 pi is constant, that is equal to 10 to the power minus 7. So one unit is Weber also, another unit is Tesla. So I have already introduced the unit for Tesla for the magnetic field. Now Weber is the unit for the magnetic flux. Similar to the electric flux that is defined for the Gauss law, here also I should define another flux parameter that is for the electromagnetic flux. So we define the electric flux phi E is equals to integration of E dot B. Similar to this, I define the magnetic flux phi V that is equals to integration of B vector dot B. Okay, so both are same, but the concept is somewhat different. One is for the electric flux and is for the magnetic flux. So if I calculate the magnetic flux unit, we know that B is Tesla into area is meter square. So Tesla into meter square is the unit for the magnetic flux, and that magnetic flux is also known as the Weber. So Weber is the unit for the magnetic flux. So for that I can write the Tesla into meters. So we know that mu naught has the dimension of Tesla into meters nearby ampere. So instead of writing Tesla into meter, we can also write Weber per meter ampere. Okay, Weber per meter ampere. So Weber per meter ampere is another unit of unit by 4 pi or dimension the unit. Okay, 1 Weber is nothing but the 1 Tesla into 1 mass. So that is the conversion factor. So we'll introduce the Weber unit in the chapter of magnetic flux. So before that, I will just giving some kind of idea so that we can relate how electric flux and magnetic flux are related. So both are being calculated in the same concept. So in order to calculate the electric flux, I should use the electric field vector. And in order to calculate the magnetic flux, I should use the concept of magnetic field. So that's why this is known the magnetic flux and the first one is the electric flux. Okay. Now, regarding the direction, I have already said that if a current carrying wire is given, so for that wire, so let us say the current is being flowing in this direction. So place the thumb along the I direction. Place the thumb along the I direction, and once I curl my finger, so finger will show the direction of the magnetic field. So I can draw n number of magnetic field lines, circular lines along this wire. But all the circular lines represent the magnetic field at that particular line. Let us say I draw two different points A, B, and C. Okay, so these are the three different points on the loop system. So since point A is closer to the current carrying element, I can say the magnetic field observed at point A is greater than the magnetic field at point B, greater than the magnetic field at point C. That means the point which is closer to the current carrying wire gives a value of magnetic field which is of more strength. As I am moving away from the current carrying wire, so magnetic field value will gradually decreasing and ultimately goes to 0. Okay. So at infinite distance away, when we move away from the infinite distance from the current carrying wire, I can say that B is almost tending to 0. Okay. So closer the line, the field is more. If I move away from the line, then the field will be less. Why? Because we already know that dB number is proportional to inverse proportional to R square. That means as R is small, then dB is more. That means if I am moving closer to the wire, that means magnetic field is more. If I move away from the wire, then the magnetic field is less. Okay. So this is the idea behind this magnetic field. Now same is the logic if I say the current is being flowing in the upward direction. So for upward direction, if I place my thumb along this direction, if I place the thumb along this direction, along the vertical direction, and if I stretch the fingers towards our right, if I stretch the finger towards our right, so BL cross R, place the thumb along the right direction and stretch your finger towards right. So that means this is the cross. Similarly, on the other side, if I move in this direction, so now I have to stretch my fingers towards left, keeping the thumb upward. So now on the left hand side, the magnetic field will be dot. Okay, like this way, once the current is being flowing down, so similarly I can say on the right hand side part of this wire, it will dot magnetic field. On the left hand side, it should be cross magnetic field. Okay, so every time the current and wire is separating the two different regions of magnetic field, and depending on the location of the point, I can calculate what is the magnitude of the magnetic field. But first of all, I want to understand what is the direction. Similarly, if I say this is the direction of the eye going upward, if I curl my finger, so finger curled in this direction, that means the loop line, these are the magnetic field lines, and these lines are basically the concentric circular lines. So these are circular lines, and they are concentric. And the direction should be on the right hand side cross, left hand side dot. Similarly, on the other surface, when the current is coming down, so right hand side will be dot, and left hand side will be cross. So these are the way by which you have to show the direction of the magnet. Okay. So every time the current carrying wire is separating the magnetic field in two different regions. One is the cross region and another the dot region. Okay. So depending on the location of the point, I can calculate what is the magnetic field intensity at that particular point. But on the right hand thumb analysis or the cross dot rule, I can also know what is the direction. Okay. Now come to the calculation of the magnetic field due to a straight wire. Okay. So there is a straight wire is there, which is through which the current is being flowing I. Now we want to measure the magnetic field for this current carrying wire at a point P, which is at a distance of D from the wire. Now what is this D? D is the perpendicular distance of the point P from the current carrying wire. Okay. Now let us say these are the two extreme points A and B of the wire. Now once I connect the P with A and P with B, I found that theta 1 and theta 2 are the two angles subtended by the A and B point with the perpendicular distance. So theta 1, theta 2 has to be measured by from the D length. From the D length, you have to measure the theta 1 and theta. Okay. Now I want to calculate what is the magnetic field at that particular point P using the Biot-Savart. So for Biot-Savart law, I have to apply the concept of element. So I know that if I move from this point, let us say from this point I move along this wire as y distance and took the element of dy. Okay. So let us say this is the element dy. So that dy is basically our dl. Why? Because dy or dl is the vector or the length of the wire or cut portion of the wire should be considered in such a direction so that along that direction the current is in. So I have taken the dy in the upward direction. Why? Because I is also in the upward direction. So now from this point, if I join the point P, then this will value of R. Okay, this will give the value of R. So what is R? R is the line distance between the point on the current carrying element to the point where I have to calculate the value of magnetic field. So I found the DL number, I found the R number, and what is theta? Theta is this angle. This angle I want to calculate the theta value. Let us say once I move at a distance of y, let us say this angle is alpha. So correspondingly this angle is 90 minus alpha, and corresponding to that angle is 90 plus alpha. So now I can apply this equation. So what is the dV value as per the Biot-Savart law? So equation of dV is given as mu naught I by 4 pi into dl vector into r vector mod into sine. Okay. So I am writing that dl cross r divided by mod of r vector whole cube. So this is the form of the dV. That is the basic of the Biot-Savart law. So this is the Biot-Savart law. I have to apply it according to our geometry. So for our geometry, this is mu naught I is I, 4 pi is 4 pi. Okay. Now what is dl? dl is dy. What is r? R is written as r. What is theta? That is sine of 90 plus alpha angle. Okay. Whole divided by r cube means r cube. Okay. So this is the final form of the equation. So sine 90 plus theta means cos theta. And because it is positive, why? Because it is in the second quadrant. So ultimately I am writing that is equals to mu naught I by 4 pi into r dy into cos of alpha divided by r. So one r will cancel out. So ultimately we are left with mu naught I by 4 pi into cos alpha multiplied by dy divided by r. Okay, so far so good. Now we have to reduce this variable. So in this particular equation, there are two variables. One is the r is variable, another y is variable, and alpha is also variable. So I have to replace it by a single variable. So for that, look for this particular triangle. If I look this triangle, so this is the triangle. For this triangle, so this is the d distance. So d is the base, y is the perpendicular, and r is the hypotenuse. So for that triangle, if I redraw this triangle, let us say this is r angle, this is the d, and this is our y number. And this angle I have said that is alpha. Okay. Now we can write the value of tan alpha. What is tan alpha? So tan alpha is equals to y by d. So from that y equals to how much? D tan alpha. So if I differentiate both sides, I can get the value of dy as d into sec square alpha dr. This is the value of dy. Okay. So I have to use that equation of dy. And what about r? So if I substitute value of r, so r is how much? R should be equals to d by cos alpha. D by cos alpha. Or I can write d into sec. Now use these two in the original equation. So here I am writing mu naught I by 4 pi. Okay. Multiplied by cos alpha. Cos alpha is there. What is dy? dy is basically d into sec square alpha d alpha. So d into sec square alpha d alpha. And what about the r square? R square is d square sec square alpha. So d square sec square alpha. So ultimately this sec square and numerator sec square alpha will cancels out. So one d will also cancels out. So ultimately we are getting mu naught I by 4 pi into d whole into cos alpha d alpha. Cos alpha d alpha. So this is the final value of the dB. So what is dB? dB is a small magnetic field produced by this current carrying element. Now I want to calculate the effect of the entire wire. So that means I have to integrate it. So once I integrate it, I will get the value of B. So what is B at point P? So B at point P is integration of dB, right? Integration of dB. So in that integration format, all are constant, only variable is alpha. So I am taking out mu naught I by 4 pi d out of the integration. So I am left with cos alpha d alpha. Now I have to put the integration limit. So to calculate the limit, so first we move in this direction to get the value of theta 2. And then we move in the other direction to get the value of theta 1. Okay. So in order to move, you have to get the value of theta 2, I am moving in the anti-clockwise direction. And for theta 1, I am moving in the clockwise direction. So if I say theta 2 is negative, then theta 1 is positive. Because both are in the opposite direction. So in limit, I put it is minus theta 2 to plus theta 1. Minus theta 2 plus theta 1. So what is cos alpha? Cos alpha integration is sin alpha. So ultimately I am getting mu naught I by 4 pi d into sin alpha. So sin alpha limit is from minus theta 2 to plus theta 1. So once I put sin alpha instead of theta 1 upper limit sin of theta 1, then minus of minus sin theta 2. So sin of minus theta 2 minus and plus or minus sin theta 2. So another negative sign will come out. So ultimately I am getting the value of mu naught I by 4 pi d into sin theta 1 plus sin theta 1 plus sin. So this is the final formula for the magnetic field produced by this wire at point P. So that is the magnitude value. So mu naught I by 4 pi d into sin theta 1 plus sin theta 2, that is the magnitude part. And what about the direction? So in order to calculate the direction, I have to use the cross product rule. So if I place the thumb along the I direction or the real direction, every time keep in mind that real direction should be the same as that of the current direction. So place the thumb along vertical direction and stretch your finger towards your right because P is on the right hand side. So that will give the palm to be faces inward. That means magnetic field at point P is crossed. Okay. So that will be the value of direction. And regarding the magnitude, I should use the formula that is mu naught I by 4 pi d into sin theta 1 plus sin theta 2. Okay. So now we have to apply this formula properly. Why? Because in order to apply this formula properly, you have to select the d distance. Now what is d? D is the perpendicular distance of the point from the wire. What is the point P? So from point P, what is the perpendicular distance of the wire? That gives the value of d. Okay, that gives the value of d. And what is theta 1 and theta 2? Theta 1 and theta 2 are the angles measured perpendicular and in opposite sides from this perpendicular. So you have to rotate this. So if I say this is the d length, so if I rotate this d length in this direction, then I am getting the theta 1. In the opposite direction, then I am getting theta 2. If the theta 1, theta 2 are the angles in opposite sides. Why opposite sides? In this particular example, I am measuring theta 1 in clockwise direction and I am measuring the value of theta 2 in anti-clockwise direction. That means these two are measured in opposite sides. So since these two are measured in opposite sides, I am saying that both theta 1 theta 2 are to be taken to be positive. Okay. So if they are in opposite sense, then they have to be taken to be positive number. If they are in the same sense, then we have to take it to negative. Let us do some calculation based on this equation. So this is the point AB. Let us say these are the 2 points, extreme point on the wire. So what is the D distance? D is nothing but this perpendicular distance. So that value will be our D number. Okay, that value is the D number. This is the perpendicular distance of the wire from the point B. So what is D? D is basically A cos theta. So D can be written as A cos theta. That is A root P by 2. Okay. Now what is theta 1? So theta 1 and theta 2 are the two angles out of which every time you have to ensure that theta 1 is the larger angle. Theta 1 is the larger angle. So theta 1 is the larger angle means once you rotate the D length, so you rotate by this angle. So now we are touching the point. That means you have to rotate by 60 degree. So write theta 1 as 60 degree. Now theta 2 is what? Theta 2 is again you have to rotate the D angle, D value, so that it will catch the point B. That means it is 30 degree. But since I am rotating in the same sense, both theta 1 and theta 2 are the angle measured in the same direction, same sense of rotation. That means theta 1 should be positive, theta 2 should be minus 30. Okay, that is important. So this thing has to be remembered that if I measure both the angles in the same sense, one has to be taken to be positive and one has to be taken to be negative. Now, which one is the positive number? The larger. Which one is the larger angle? That is the theta 1. Theta 1 is the larger angle that you have to take as positive, and theta 2 is the lower angle that you have to take as negative. Why? Because I am moving in the same sense. Now, using this proper value, you can use it in the equation so that you can get the answer. Similarly, if the wire is like this way, again this is the perpendicular distance. So simply A is our perpendicular distance. And since now both theta 1 and theta 2 are measured in the opposite sense, so both are to be positive. Now theta 1 is the larger angle, so I should take theta 1 as 60 degree and theta 2 as 30 degree. Okay. So based on this information, now I can apply the formula to get the result of magnetic field due to the straight wire at point P. Okay. Now there are two variety of this problem is that I use this equation to calculate the magnetic field for a straight wire which is a finite. Why it is called finite wire? Because from the point P I can clearly see the two endpoint of the wire. Okay, I can clearly see the two endpoint of the wire, and that's why it is called the finite straight. So this wire is basically finite. Now, if the situation is like this way, now from a particular point P, you can only see the point A, but the point B is not visible. So you have to view the point B, you have to move a higher distance. This angle is tending to 90 degree. Now what is this angle? That angle is basically theta 1 angle. Why? Larger angle is a theta 1. So theta 1 is tending to 90 degree, but theta 2 is equals to 0 degree. Theta 2 is equals to 0. For this situation, this wire is known as semi-infinite. So again, if I go for the calculation to calculate the direction of the magnetic field, again you have to stretch the fingers, thumb, right hand thumb along this I direction vertically up, stretch the finger towards your right. So magnetic field at point P is the cross into the plane of ether. And once I put the value, so that is mu naught I by 4 pi d is there. But instead of writing sine theta 1, I am writing sine 90 plus sine 0. Okay, sine 90 means 1. So ultimately, I am getting that mu naught I by 4 pi. So mu naught I by 4 pi d is the magnetic field strength due to the semi-infinite wire at point P, and the direction is cross. This is cross. If I reverse the direction of the current, so then the magnetic field will be dot at that same point P. Okay, so this is the semi-infinite. Now another variety of the problem is that infinite straight wire. Infinite straight wire means now you cannot view both the points A and B. Both are not visible. So if I move in this direction, then this angle, that is the theta 2 angle, is tending to 90 degree. If I move in this direction, then also the theta 1 angle is tending to 90 degree. So both theta 1 and theta 2 are tending to 90 degree, but they are in opposite sides. So for that situation, both are to be positive one. So this is sine 90, this is sine 90 means 1 plus 1 means 2. So ultimately I am left with mu naught I by 2 pi d. So very important result regarding the magnetic field strength for a infinite. This is an infinite wire, and for infinite wire, the magnetic field at any particular point P, which is equals to mu naught I by 2 pi d. But for semi-infinite wire, it is mu naught I by 4 pi d. Mu naught I by 4 pi d. Okay. Now let us do this one. So let us say there is a wire which is at an angle of 37 degree with respect to the x-axis. Now first you identify that two endpoint of it. So one is A and the B is very far away. B is very far away. Now this is the point P where you have to calculate the magnetic field. So for that you have to draw the perpendicular distance. So what is the perpendicular distance? So from point P you draw a vertical line. So that number will be the value of D. That number will be the value of D. Now this distance is basically the A distance given. See, that angle is 37 degree. That means this angle is 90 degree. So that means this angle is 53 degree. This angle is 53 degree. So D becomes how much? D becomes A sine 53. What is D? D is A sine of 53. So sine 53 means 4A by 5. So 4a by 5. Now you have to rotate the d vector or the d length in the direction of a. So if I rotate d, then that means this is the angle has to be rotated to touch the point a. And in order to touch the point b, we rotate by this much angle. So this angle is how much? This angle is almost 90 degrees. Okay. So larger angle, that is theta 1, is equals to 90 degrees. And what is theta 2? This is a smaller angle. Theta 2 should be how much? That is 53 means 37 degrees. But again, since I am moving in the same sense, this number is positive, this number is negative. Okay. Because both the angles are moving in the same direction. Both theta 1, theta 2, I am moving. In order to measure the theta 1 and theta 2, I have to move in the clockwise direction. So since I have to move in the clockwise direction for both the angle, so I am saying that theta 1, theta 2 both are not with same sign. Larger angle theta 1 is a positive, theta 2 is a negative. So now I can put the value in our equation. So equation is V equals to mu naught I by 4 pi d into sine theta 1 plus sine theta. What is the formula? Now I am putting the value inside this. So that should be equals to mu naught I by 4 pi. What is d? D is 4a by 5. So 4a and the numerator 5. Now what is sine theta 1? Sine theta 1 is sine 90. That means sine 90 is 1 and sine theta 2 is minus 37. So minus 37 is minus 3 by 5. Minus 3 by 5. So ultimately I am getting 2 by 5 in the bracket part. So mu naught I 1 5 is there. The 4 pi into 4a into 2 by 5. So this 5 will cancel out. This 5 will cancel this one. So ultimately we are left with 8. So mu naught I and 8 pi a. That will be your answer. So that the magnitude part, regarding the direction, stretch the thumb along this I direction. Yeah. Put your thumb along the I direction, stretch the finger towards your P point, that is along D direction. So palm will be facing towards the plane, into the plane of paper. So magnitude is this one and direction is cross, means into the plane of paper. That's all. This is the answer. Okay. So whenever the wire is inclined, every time or any other orientation, first of all try to calculate the D. Once you get the value of D, then try to get the information about the theta 1 and theta 2 angle. So theta 1 and theta 2 in this particular situation, both are in the same sense. So one has to be positive, another has to be negative. Okay. So like this way, let us say this problem. Okay. So a wire carries a steady current of 50 ampere ratio. Steady current of 50 ampere. So I value is given. Find the magnetic field to be used by a 1 centimeter segment of this wire at a point P2, which is 1 meter away. So this 1 centimeter is nothing but the DL. Okay, 1 meter is our R number and this is I number. So I can apply the Biot-Savart law to calculate the magnetic field at point P, that is dV. dV is how much? Mu naught I by 4 pi into dl vector cross r vector mod of this number divided by r vector cube. Okay. Now what is dl? dl is 1. What is r? r is 1. And theta is what? Theta is the angle between the dl and r. So that number is theta. So these are dl vector, these are dl vector, and these are dr vector, r vector. So angle between the dl and r is a theta. So theta is sine 37. Okay, now I can put this value. So mu naught is mu naught. I is how much? I is basically given as 50 ampere. Here by 4 pi into dl. dl is 1 centimeter, means 10 to the minus 2 meter into r. r is 1 meter into sine of 37. Sine 37 means 3 by 5. Divided by how much? 1 cube. 1 cube. Okay. So mu naught is 4 pi into the minus 7. 4 pi into the minus 7 into 50 into 10 to the power minus 2 divided by in 1 by 3 divided by 5. So this 5 cancels out. So again another 4 pi is there. So I am left with this 5 will cancel out. So ultimately 3 is there. 3 is there. So 3 into 10 to the power minus 7 minus 8 minus 8. 3 into minus 6. So minus 7 is there, 1 0 is there, 10 to the minus 2. That means 10 to the minus 1. 10 to the minus 1 means minus 8. Okay. So 3 into the minus 8 Tesla. Now this can be written as 30 into 10 to the minus 9. That means 30 nanotesla. That means 30 nanotesla. That will be the answer. Now regarding the direction, so place your thumb towards LDL dip and stretch your finger towards the, so palm will be outward. So 30 nanotesla outward will be your answer. That is the answer. Okay. So this is a simple application of the Biot-Savart Law directly. I am not using any kind of formula because in order to apply the formula, both the angle theta 1, theta 2 should be known to you. But instead of knowing the theta 1, theta 2, in this question, the DL is directly given. DL number is directly given. So for that element, you want to calculate. So that means you want to calculate the DB number, not for the entire wire and not for the entire wire. So this is the situation of direction of magnetic field at point P. Now this is an infinite wire. Both are infinite. So both are infinite means B at point P should be equals to mu naught I by 2 pi D. That is our answer. But regarding the direction, since the current is going downward, so place the thumb downward and stretch your finger toward P. So now the field line will be dot. So mu naught I by 2 pi D or 2 pi R dot. Dot is the field strength, direction. Okay. Similarly, this question. Okay. Now let us see this question. So a horizontal overhead power line is there, which is at a height of 4 meters from the ground. Okay. And carries a current of 100 ampere from east to west. So current carrying wire is carrying the current from east to west. The magnetic field directly below it on the ground. Okay. Let us say this is our ground. This is the ground. So at a height of h, that is equal to 4 meters from the ground, a wire is there and the wire is carrying the current from east to west. So this is the direction of east, this is the north, and this is south, this is west. Okay. So wire is carrying the current from east to west. So east to west means in this direction the current is being flowed. So this is the I value. Okay. Now we want to calculate what is the magnetic field strength at this point P, which is at a distance of 4 meters below the wire. So first of all, check the direction. So what is the direction? So stretch the thumb, place the thumb towards the I direction and stretch the finger vertically downward. So palm will be facing towards south. So magnetic field at point P should be towards south. So this is the direction of the magnetic field at point P. So B should be in this direction. So towards south is this one, towards south. So first of all, cancel out this A here, option D and D. Now check for the value. So B will be due to the infinite. B will be the value due to infinite where. So ultimately your answer should be mu naught I by 2 pi. That is the formula. So mu naught is 4 pi into 10 to the minus 7. Minus 7. I is how much? I is 100 ampere. Thereby 2 pi into D is how much? D is again 4 meter. Okay. So ultimately 2 pi cancels out. So 2 by 4 is 1 by 2. So means 5. So 5 into 20. 2 pi 2 by 4 is 5 into the minus 6. 5 into the minus 6 Tesla towards the southward. Okay, that is the direction of the magnetic field line below, vertically below at a distance of 4 meters from the wire itself. Okay, so you have to draw the diagram properly and then only have to answer. Okay, then only have to answer. Now this is the part of the wire. Let us say this is the part of the wire AB wire is there. Now we are asked to calculate the magnetic field at point P. So this is a finite wire. So for finite wire, this is the D distance. So D is this one. Now regarding the theta 1 and theta 2, so I simply say that theta 2 number is 0 degree and theta 1 is this angle, theta 1. So that is 45 degree. Okay. Now using the formula, I can write that B at point P should be equal to mu naught I by 4 pi D into sine theta 1 plus sine theta. That is the formula. And regarding the direction, sine theta 1 plus sine theta 2. Direction at point P will be crossed. Okay, at point P will be crossed. So A and B options are discarded. A and B. So in order to answer this type of question, first of all check the direction. So once you got the direction, then according to that, you cancel out the options. So first straightforward calculate the option A and B. You don't have to look about the option A and B. Straightforward calculate the magnetic field at point P. So magnetic field at point P, this formula is mu naught I by 4 pi L. B is a basically L number. And sine theta 1 is sine 45 degrees 1 by root 2, and sine theta 2 is sine 0 degree 0. That will be your answer. So mu naught I by 4 pi or 4 root 2 pi L. That will be your answer. That is option number C. And I have already checked that the direction is proper. So option C will be your correct answer. Okay. So this is not the infinite wire, this is a finite wire, but it is a part of the wire AB. Okay. Part of the wire AB. Now it is infinite. Part of the wire is infinite. Okay. So if I say this is the point P, so that means this is our D distance. Again the point P magnetic field is proper. So eliminate the option A and B. Eliminate the option A and B. So look for option C and D together. So this is the L, that is our D distance. Now regarding the point P, A, so this angle is theta 2. Why theta 2? Because theta 2 is lower angle 45 degree. And theta 1 is how much? Theta 1 is the for the point B, which is at a distance of 90 degrees. So theta 1 is 90 degrees. Okay. And since both are in the opposite sense, that means both are angle be positive. So directly I can write the answer mu naught I by 4 pi D, so 4 pi L into sine of 90 degree means 1 plus sine of 40 degree means 1 by root 2. Okay, so that will be your answer. So option number C is the correct one. Okay, similarly, so this is the same situation where the angles are basically given 45 and 45. So that means I can clearly say that this angle is also 45 degree. This angle is also 45 degree. Okay, so both theta 1, theta 2 are same, that is 45 degree. And at point P, again the magnetic field is cross. So cross means either A and B are not possible, only option C and D are left. So B at point P should be equals to mu naught I by 4 pi L, 4 pi L into sine of 45 plus sine 45, means 1 by root 2 plus 1 by root 2. So 2 by root 2 means root. 2 by root 2 means root 2. So mu naught I root 2 by 4 pi L. That is your answer. Okay, mu naught I by. So by cancelling root 2, you can get to root 2. Okay. So cancel root 2 from the numerator and then we denominator in the 2 root 2 part. Okay. So mu naught I by 2 root 2 pi. This is the answer. Okay, this is the answer. Now there is another situation where, so there are two very long means it is an infinite. So very long means infinite wire, straight and insulated wires are kept at 90 degree angle from each other in the XY plane. So they are in the XY plane as shown in the figure. These wires carries current of equal magnitude. So through this wire both the currents are I and I. Now whose directions are shown in the figure? Okay. So the net magnetic field at point P. So in order to calculate the net magnetic field at point P, what you have to do? So for point P, so let us see this is the wire number 1, this is the wire number 2. So for the wire number 1, magnetic field at point P will be dot. So B into 1 will be dot. For wire number 2, B will be 2 at point P will be cross. Okay. So that means B at point P, so B at point P should be equals to B1 minus B2. That is the net. Why minus? Because 1 is the cross and 1 is the dot. So what is B1? B1 is simply the value for magnetic field at a distance of D from an infinite wire. So for infinite wire it is mu naught I by 2 pi D. Same formula because D is the distance of the point P. So minus of mu naught I by 2 pi D. Both the wires are carrying the equal current. So both will be cancelled. So ultimately the net is 0. So net magnetic field at point P is 0. That will be the answer. Okay. So since both are infinitely wire, so at point P I am using the same expression of magnetic field for both the wires. And since both the wires are carrying same current, I and I both, okay, that means they will cancel each other. So there will be no net magnetic field at point P. Similarly, this is another type of variety of question where there are two conducting wire AOB and COD are placed right angles to each other. Let us see, this is the one wire, this is the another wire. This is, let us say, this is the AOB wire, this is COD wire. Okay. the wire AOB carries the electric current of I1. So for the wire AOB, this is the direction of the current I1. Okay. And there is a current carrying by CO2 is I2. Let us see the I2 current that is there. Okay. The magnetic field on a point lying at a distance of D from O. Okay. So from point O, D in a direction perpendicular to the plane of the wire AOB and CO. That means, so if I say the wire I2 is, let us say, along x-axis. Let us say along x-axis. And I1 is along, let us say, y-axis. So D is the point which has to measure in the Z direction. Because Z axis is the perpendicular to both the axes. So D is the distance of the point P from the O point which is perpendicular to both. So this is the D point. Let us say this is the point P where you want to calculate. Because this distance is D for both the wire. Both the wire, this is the D distance. This distance is D. Okay. Now, at this point, if I want to calculate the magnetic field due to I2 wire, so place the thumb along X direction. Place the thumb along X direction and stretch your finger toward Z direction. So palm will be pointed downward. Downward means what? Downward means y-axis. In this direction. Okay. So not the, so this one should be the y-axis. This is the negative y. Let us use the y-axis, y positive, and this is y negative. So at point P, let us say I am giving the name as this is the point P. So for the wire I2, for wire I2 is carrying the current along X direction. So place your thumb along X and stretch the finger towards Z. Stretch the finger towards Z. So the palm face will vertically downward. So this is the B1 direction. So let us say this is the B2 direction. Okay. So in the vector notation, what you should write? B2 vector should be equals to how much? B2 vector should be equals to mu naught I2 by 2 pi d into J with a minus sign, minus J. Okay, because it is negative direction. So similarly, for the I1 wire, place the thumb along the negative Y and stretch your finger along the Z direction. So palm will be facing towards our negative x-axis. So negative x-axis means in this direction. So this is the B1. This is the B1 vector. Okay. So what is the B1 number? So B1 should be equals to B1 vector should be equals to again mu naught I2 by 2 pi d but with a minus I cap. So net magnetic field at point P should be the vector sum of B1 plus B at point P should be equals to vector sum of B1 plus B2. So you are asked to calculate the mode of this number. So square both the terms. So ultimately what happened? It should be equal to root of I1 square plus I2 square. And constant part is how much? Mu naught by 2 pi d. So mu naught by 2 pi d. So that will be your answer. Mu naught by 2 pi d, the root of I1 square plus I2 square. That is option number C is the correct. Okay. So you have to apply the concept of vector also, so that in some situation the problem may be in the 3D coordinates. Once the wires are placed in a 3D coordinate system, so you have to properly show the direction in which axis. So whether it is positive X or negative X. Because in this situation, the direction of current is not known. So it has been only saying that the current is being flowing across the wire, across the wire. Okay. So the direction of the current is not properly known. So I assume that the direction is in the positive x-axis or negative y-axis. Now, along with that direction chosen, I want to calculate the magnetic field at point. And once I calculate the magnetic field at point P, I am getting the two different vector. One is aligned along the x-axis, another aligned along the y direction. Net vector should be the square root of these two. Because those are the two perpendicular components. Yeah, those are the perpendicular components. Okay. So let us do this one. So there is a finite current carrying wire of length 2L. So total wire length is 2L. That is bent into an L shape. Into an L shape. Let us use the point A. This is the point O. This is the point B. Okay. So one wire is AO, another wire is BO, and such that you want to calculate the magnetic field at point P, which is equidistant from both the wire at L by 2. That means this distance is L by 2. This is L by 2, and this is also L by 2. This is also L. So for AO wire at point let us use the wire number 1. For V1, V1 should be cross. Similarly, for the wire number 2, I2, V2 should be again cross. So that means both the vectors should be added together. So B at point P should be equals to V1 plus. So so since both B1 and B2 are symmetrical figure, so I want to calculate only the B number and then multiply by B. Okay. So in this situation, this angle is 45 degree. This angle is also 45 degree. So for B1 number, B1 is what? B1 is mu naught I by 4 pi d. So 4 pi d. D is what? L by 2. L by 2. Into sine theta 1 plus sine theta 2. That is 1 by root 2 plus 1 by root 2. Okay. So ultimately we are left with mu naught I by 2 pi L into 2 by root 2. That means mu naught I by root 2 times pi L. Okay, that is the B due to one single wire. Now B1 and B2 both are magnitude same. So ultimately it should be 2 times of mu naught I by root 2 pi L. That means I am getting root 2 times mu naught I by pi L. Root 2 times mu naught I by pi L. And direction I have already checked that is cross. So option B is the correct one. Option B is the correct one. So every time if I got the idea about the symmetric figure, so this is another symmetric figure. So you want to calculate the magnetic field at point P. So simply calculate the magnetic field for the AB. Because for entire loop, the current is going in the clockwise direction. So whatever the magnetic field that will be at point P is the cross. So all the wire will be added up. Okay. So I can write simply V at point P should be equals to 4 times V due to AB wire. 4 times V due to AB. And ultimately direction is also cross. Okay. By seeing this cross direction, first of all, eliminate the option A and B. A and B cannot be your option. Why? Because the answer is on the cross point. So for the AB part, so join the A point and B point with P point, and P is what? P is just symmetrically point, that is at a distance of L by 2 again. So this angle is 45 degree. This angle is also 45 degree. Okay. So final answer should be how much? Final answer should be 4 times of B at point. So mu naught I by 4 pi D, and D is L by 2. So L by 2 into 1 by root 2 plus 1 by root 2. Okay. So ultimately get 2 by root 2. So 2 to the 4. So 4 cancels out. So 4 into mu naught I by pi L into root 2. Root 2. So that will be our answer. That will be our answer. So not correct one. So 4 mu naught I. So 4 cancels out. So 2 by root 2. 2 by root 2. 2 root 2. Okay. 2 root. Okay. It should be 2 root. 2 root 2. So that means option number D. 2 root 2 mu naught I by pi. That is the correct answer. Okay. Similarly, this is also a regular figure. So regular hexagon is there, and you want to calculate the magnetic field strength at point P. Again, the current is being flowing in the anti-clockwise direction. So whatever the magnetic field at point P, that should be drawn. So straight for answer of the option C and. Okay. So let us say this is the one single wire AB. So total magnetic field at point P. So B at point P should be 6 times the magnetic field due to wire A. So you only have to calculate the magnetic field for the wire AB, and then you can add this. So for this is the perpendicular distance D. You join these 2 points. Okay. So a regular hexagon is making an interior angle of 120 degree. So these are the half angle that is 60 degree. This is also 60 degree. But these are theta 1, theta 2. Both are in the opposite sense. So these angles are 30 and 30. Okay. So here theta 1 and theta 2 both are equals to 30 degree. And both are in opposite sense means positive. And what about D? So D is nothing but the AP sine 60. So D is what? D is AP sine 60. What is AP? AP is the side length. Because ABP is an equilateral triangle. So AP is what? AP is L. So L root 3 by 2. L root 3 by 2 is our D number. L root 3 by 2 is our D number. So once I got the value of D, now I can put it in the calculation. So it should be 6 times mu naught I by 4 pi D. D is what? D L root 3 by 2 into sine 30 plus sine 30. Sine 30 means half plus half. That means this bracket is 1. So ultimately we are getting 2. So 2 means C mu naught I by pi L root 3. That means root 3 mu naught I by pi. That will be our answer. Root 3 mu naught I by pi. That will be our answer at the magnetic field at point P. Okay. So whenever you encounter with a regular figure, so mind it that the total effect will be the summation of all the effects added. Okay, that means if I want to calculate the magnetic field into one wire, so multiplied by 6, that will be the total magnetic field at that particular point P. Okay. So now it has now that the magnitude of the magnetic field at the center of an equilateral triangle of loop of 1 meter, which is carrying a current of 10 ampere. So center means the centroid part. So this is the ABC is the, let us say, this is the where, and I don't know in which direction the current is being flowing. Let us say in arbitrary direction current is being flowing. So this is the point P where you want to calculate. So again I have to calculate the one wire and then add this. So for one wire, if I draw this perpendicular, this is our D distance and these are the angles. Okay. So this angle is 30 degree. So this theta 1 and theta 2 both will be equal to how much? 60 degree. First of all. And what is D? D is basically the 1/3 of the height of the equilateral triangle. Why? Because the E point is the center point. It will divide the entire height into 2:1 ratio. So I write the D number as equals to 1/3 of the height. Height is what? Height is A sine 30. Not A. You write it A, yes, A sine 30. A sine 60. Okay. So A is the side length. A is the length AB. So this is the A length. So A sine 60 is the height part. So 1/3 of that height will be the value of D. So sine 60 is root 3 by 2. So ultimately I am getting A root 3 by 2 into 3. So 1 root 3 cancels out. So A by 2 root 3. That is the D number. Okay. Now if I rearrange the values, so ultimately what I am getting, so B should be equal to 3 times of B due to, let us say, BC. So 3 times of BC where means mu naught I by 4 pi D. D is what? A by 2 root 3 into sine theta 1 plus sine theta 2. Sine theta 1 plus sine theta 2 means both are 60 degree, means root 3 by 2 plus root 3 by 2. So ultimately I am getting root 3. So mu naught I by 4 pi A into 2 into root 3, and root 3 means 3 into 3. Okay. So mu naught is 4 pi into 10 to the minus 7 into I into 2 into 9 by 4 pi A. So 4 pi cancels out. So 9 into 2 means 18 into 10 to the minus 7 into I by A. Now what is I? I is 10 and A is 1. So 10 comes into the figure. So 18 into 10 to the power minus 6. That is 18 microtesla. 18 microtesla will be your answer. Okay. So this is how we have to apply the concept of calculation of magnetic field into plane wire, straight wire. The wire may be finite, maybe infinite, maybe semi-infinite. Depending on that, you have to do the calculation.